We're going to visit a few other properties of the Fourier transform and then finish up talking about filtering and hopefully modulation today as well. So first of all, a property called Parseval's. Oops. Parseval's theorem. And this says that the energy of a signal is the same in time or frequency. Let me see if I can type that here. All right, so what do we mean by that? Well, we mean that energy of, let's say, x of t, that this could be calculated as the integral from negative infinity to infinity of the magnitude squared of the Fourier transform of x. So we defined it originally as the integral of the magnitude squared of x itself. So this would be in continuous time. In discrete time, we have that the energy of some discrete time signal is almost the same, but you integrate from negative half to half, or from 0 to 1. Why is it different? Why do we integrate from negative half to half? What is it? Yeah, go ahead. Yeah, right here. Yes. So in discrete time, the Fourier transform is always periodic. You just integrate over one period. Okay. You have something similar for the Fourier series. So let me first mention, you guys will do this in the homework assignment that I'll distribute to you soon. You'll prove this in your homework. And I'll give you the steps needed to show this. It's actually very simple from properties you already know. It's just this formula. The physical meaning, now that we have Parseval's theorem, is that it is actually the time domain energy as well. So if you viewed the frequency domain and calculated energy as if it was a time domain signal, you'll get the same thing as if you had done it to the actual time domain signal. Okay, so then you have if x is periodic, period t. Now we're going to have a Fourier series property, and that is that the energy, the power now, because we're not going to talk about energy of a periodic signal, the power x of t is going to equal the sum k equals negative infinity to infinity of the square values of the Fourier series coefficients. Okay, and that was for continuous time. And for discrete time, it's going to be just a sum over one period. K equals 0 to n minus 1. Remember, the period for the discrete time Fourier series is just the same as the period for the time domain, capital N. Now, I will give you a little bit of an argument for why this is true in the Fourier series. Here we go. X of t, we said, can be written as a sum, k equals negative infinity to infinity, of ak e to the I 2 pi k over t, t. That's the synthesis equation for the Fourier series. Now, you did a homework, a problem in your first problem set where you had to calculate the power of something looking like this. Okay, and it turns out that you get, so if you look at the magnitude squared of x of t, you're going to get some terms, you get a bunch of cross terms. You're going to multiply this by its conjugate, right? So I'll write that out here. You have a sum over k, from k equals negative infinity to infinity, ak e to the I 2 pi t. And then you have times its conjugate. I'll bring the conjugate inside here, so you get sum over from m equals negative infinity to infinity, am conjugate e to the negative I 2 pi k over t t. Now, there's going to be, if you take the term where the terms where k equals m first, then that's going to equal something like this. Sum k equals infinity to infinity. Squared. And then you take all the cross terms, so I'll say plus cross terms. By that I mean all the points in the sum where k does not equal n. Okay, so let me say here k equals m, k does not equal m. And each of these over here, the cross terms all are going to have an e to the I 2 pi something up here. I'll say I'll just say m. Well, no, I don't want to use m. I'll use r over t, where r is an integer not equal to 0. Okay, now what we find is that when you do the integral of this, to calculate power, you integrate this and normalize. And you only need to integrate over one period. But when you integrate any of these, you get 0. So the cross terms do not contribute to the power. This comes from the fact that they are orthogonal, that these signals are orthogonal to each other. So only the power ends up splitting, that only the same terms from each side contribute to the power calculation. Okay, so we just got back our power here. If we have a constant, then that equals the, if we integrate a constant, you integrate this, you get 0. You integrate this and normalize by the width, you're just going to get this constant back. All right, same thing for discrete time. So, okay, so we've sort of discussed where Parseval's comes from for the Fourier series. The Fourier transform, like I said, you'll do that in your homework. Is there any questions about this here? Why these are 0? You see why each one of these cross terms is going to have an exponential with a non-zero frequency, with an integer here. So when we integrate, so what we're going to do in the end here is we're going to say integral from 0 to t, 1 over t, that's going to equal this first term here, which is just going to come out because it's constant, plus, and you're going to get some sum, and you're going to have an integral from 0 to t. Let's say 1 over t here. This sum for all terms and all cross terms. and you're going to get an integral of, you get something here, I won't fill it in, some constant. You're going to integrate an e to the I 2 pi r over t, tau d tau. All right, now let's just look at that integral right there. Okay, so that equals 1 over I 2 pi r over t, I 2 pi r over t, evaluated from 0 to capital T, and then this is just going to be, pull this part out, T, and we're going to get a e to the I 2 pi r minus e to the 0. Okay, and this is 1 and this is 1. So these go away. So that's a nice property. This actually generalizes. This Parseval's theorem isn't just for the Fourier transform. For any orthonormal transformation, you're going to get this property where the energy is just the sum of the energies of in the new domain. Okay. Now I'm going to show you a property of the Fourier transform, which you will use to prove this in your homework. But I'm just going to state it as a Fourier transform property here. So we already saw a couple of things. We saw that that related to conjugates and symmetry in the Fourier transform. So we've already seen this stuff. That x of negative t, when you transform that through the Fourier transform, you get just the flipping in frequency of the Fourier transform. That's true in general. And we saw that if x of t is real, then we have conjugate symmetry. X conjugate of negative f equals x of f. We call this conjugate symmetry. And we also, let's see, we also saw something about the real and even odd decomposition. Okay, so x of t, if we want, we can split this into two parts, an x, let's say, real of t, and an x imaginary of t. And each of these we can split, again, into an x real and even part of t, x real odd part of t, x imaginary even, and x imaginary odd of t. So we talked about decomposing a signal into an even and an odd part and a real and imaginary part. And if you just do this in sequence, then you get 4 parts. You get, I'll write these out, real and even, real and odd, imaginary, even, imaginary, and odd. So there's a unique way to split any signal up into these 4 components. Now, what you saw, what you did in problem set 3 was you played around, you showed that the Fourier transform of of a real even part, or of a real and even function is real and even. And the Fourier transform of a real and odd part is it's imaginary and odd. And it's not hard to show once you have that if you multiply an I by a real and even function, you now have an imaginary and even function, and you can get this next property very easily, that x of an imaginary and even function must keep its even property, but stay imaginary. And if it's imaginary and odd, again, it changes. It's from being imaginary, it changes to being real, and stays odd. Okay. Does this look familiar to anyone doing these properties? Yes, some people. Okay, so it was. I think this was given as an exercise. So, I mean, the way to remember this is simply that odd functions, they're the ones that change from being imaginary to being real when they go forward or backwards through the Fourier transform. In fact, this is an easy way to show the conjugate symmetry, because it means any real function only has these two parts. And that means that its Fourier transform must be made of a real and even function and an imaginary and odd function, and from that you get the conjugate symmetry property. Okay, so what I want to show, though, is that this property, x conjugate, sorry, the Fourier transform of x conjugate of t, when you do the Fourier transform of that, you get x conjugate of negative f. A little bit strange. You get the conjugate there, but you also flip it in frequency. Well, how can we get that? Well, notice that x conjugate, so this is the property. This is the new property I wanted to show you. A little proof here. X conjugate of t equals x real of t minus x imaginary of t. Conjugate just means you change the sign of the imaginary part. That equals x real even of t plus x real odd of t minus x imaginary even minus x imaginary odd. That means that the Fourier transform of x conjugate of t equals the Fourier transform of this whole side here equals the Fourier transform of x real of t. Actually, I'm just going to write that as a capital X. X that came from the real even part in time. You have to just remember that this subscript now, RE, does not mean that capital X is real and even. It means this is the Fourier transform of this. This is real and even in time. Okay? Plus X real odd minus x imaginary and even minus x imaginary and odd. Now what we're going to do is we're going to notice a couple of things. This here What do we know about this guy? Well, if it was real and even in time, then it is real and even in frequency. What do we know about this? It was real and odd, so now it's imaginary and odd. And this one is going to be imaginary and even. This one is real and odd. Okay, now let us use the property of let's use the property of even and odd to put in a negative f. So that means that if I change this to negative f, because it's even, this part is even, then changing the negative f does not change anything. So x RE of negative f. And now this part is odd. So if I put a negative f in here, I have a negative out front as well. That's the definition of an odd function. So I should say minus x real odd of negative f. And here I have even again, so I can do minus x imaginary even of minus f. And then a plus x. So you see I just used the properties of odd and even to do that step. And now I'm going to say that for a real, now I'm going to use whether they're real or imaginary for the next step. I'm going to say if it's real, then it equals its conjugate. And if it's, and then here, because it's imaginary, then then it equals negative its conjugate. So I change the minus to a plus, and I can stick a conjugate on there. This step, does this make sense? How did I get rid of the minus sign here? It's imaginary. So taking a conjugate of an imaginary signal is the same as negative that function. Okay, that's what a conjugate is for an imaginary function. So then I have here plus, again, this one's imaginary, so plus, and this one's real, so I stick the conjugate on there for free. And you see that we're done. Those are just the conjugate of the whole thing. X real, x minus f, plus x. X. Okay, so we got our property. You will use that when you prove Parseval's theorem, and I will give you plenty of hints on how to use it. Okay. All right, let's see what next. Oh, I know what's next. Sometimes this is called periodic. Okay, we're going to talk about circular convolution. We know what convolution is. I'm going to define something that's a lot like it, a little bit different, and we'll see that it's important to know this distinction. It will play a role in the analysis of systems. So there are several interpretations of circular convolution, and I'll go through all of them. So 1, suppose that of t and y of t are periodic with the same period. Now we want to define a convolution of these two signals, two periodic signals. But if you use regular convolution, you will not get a meaningful result because the integral will not evaluate to a finite number because it's periodic. You do a flip, you do a shift, multiply, you get some periodic thing and try integrating that from negative infinity to infinity. That doesn't work. So one way to think of this is if they're periodic, in most cases the convolution will be infinite for all t. That's not very interesting. But we can define the circular convolution in this case to be, we write x of t convolution with the circle around it. Actually, and in this case, the name periodic convolution is justified. I usually hear it referred to as circular convolution, but it can go by either name, and for this motivation, periodic convolution seems to make sense. You have periodic signals. What we're going to do is say that this is the integral of x of tau, y of t minus tau, d tau, but over one period. Okay, that's the only difference. So this here. So why do we want to define such a thing? Well, it turns out we talked about a multiplication property of signals. What's the multiplication property related to the Fourier transform? If you multiply two signals together, what happens? What? Convolution in frequency. Yes. That's true for continuous time. Okay. So let's revisit multiplication property. Okay, continuous time, x of t, y of t, when you transform them, you get x of f convolved with y of f. But in discrete time, that's not true. And one way you would know that it's not true is because if you assumed it was true, you would get the convolution of two periodic signals. You would get infinities, and you'd say, wait a minute, this is a well-defined signal. It should have a Fourier transform. Why am I getting infinities when I try to calculate Fourier transform? It's actually not true in discrete time. But what is true, as you could guess, is that it's x of f circular convolved, a periodic convolution with y of f. Now, I'm going to put a little subscript 1 here, because really, circular convolution is defined over one period, and we should specify what the period is. Now, true, if these both have the same fundamental period, then leaving the subscript off should mean that I use the fundamental period of these signals. Okay. But anyway, so there's the multiplication property. Now, I'm not going to explain why this is true. You know, for this one, we could get it straight from duality. We already knew that convolution in time was multiplication in frequency. We have a very nice duality property. Duality for discrete time is a little bit different. Maybe some of you have thought about that because that was in one of the problem sets. And so we won't justify exactly why this is true. But at some point, we will talk about thinking about discrete time signals in continuous time. Actually, that will be next week. And some of the nuances of the Fourier transform may be a little more clear once you think about discrete time signals in continuous time. Okay. Okay, I said there were more than one interpretation of this circular convolution. Let's do interpretation 2. All right. Suppose that x of t is periodic, and y of t, in fact, I'm going to use h because that'll motivate this in a minute. H of t is finite energy. It's an energy signal. Okay. Now x of t convolved with h of t, the regular convolution, is well defined, right? So, no need for circular convolution here. However, you'll notice the mathematics works out to be equivalent to the following. Define periodic summation Let's say the periodic summation of any signal, we'll use capital T as a subscript to represent this, is just an infinite sum h of t plus k capital T. All right, what have I defined here? I'll put a box around this because this is kind of a separate definition. Okay, so what have I done here? I've taken something like, let's say there's h0, let's say 2, and let's say that's h of t. Then that means that h of 1 t, the periodic summation of period 1, is going to result in this plus this plus this, and so forth all the way both directions. Add them all up, and you're going to get something that looks like, hard to say, but all right, so this would be h1 of t. And here's the axis, just to make that clear. I'll put the axis here as well. Okay, is it clear what I did? I'm just adding up infinitely. Many of these shifted by the period that I want. The result will always be periodic. So H1 will have period 1. Okay. This is like the periodic extension we talked about at the beginning. What's the difference between this and the periodic extension of a finite duration signal? What's the difference? Yeah? Yeah, it doesn't have to be equal to H, even if you look at just the same spots where H was defined. How is it related to the periodic extension? Yeah? Yeah, so if H was only contained on the interval from 0 to whatever my period I wanted, 0 to 1, and then was 0 everywhere else, if it was finite duration within that limit, then it would be equal. The periodic extension, the periodic summation would be equal. Let me see. equal if H finite. Okay, so if the duration of H was less than or equal to T, then it's the same thing. Okay, so why did we define this thing? Can anyone guess where I'm going with this? Here's where I'm going with it. X of T convolved with H of T equals X of T with H T of T. Okay, so this is the regular convolution of this periodic signal with something is the circular convolution, the periodic convolution of X with the periodic summation of the other one. Okay, this okay, let me give the last interpretation. So this is one interpretation of what a periodic convolution is. It's a regular convolution of the periodic, of one of the periodic signals with one period of the other signal. Okay, so you could always just say, so it turns out that if you convolve a periodic signal with something that maybe has length greater than the period, they're actually, all that actually matters in the calculation is the periodic summation of H. So that's actually interesting to think about. You could have two different H's here. Think of this as the impulse response of the system. You can have two different impulse responses. As long as they have the same periodic summation, then the result of the convolution of your periodic signal will be the same with either of them. So it's kind of interesting. Oops. All right. Suppose that X of T and Y of T have duration T. So now we're not going to assume that they're periodic. We're just going to say they have a finite duration. Yeah. Yes. This should be the same period. So I'll put that here. Good. Okay. Now suppose that we think of we have two finite duration signals. Then we can talk about their circular convolution as being when I say duration T, we'll assume that they are on the set 0 to T. That's where they're defined. Okay. Then what we can do is look at these, is we can define circular convolution here between these equals I'm going to say 1 period of xt of t circularly convolved with yt. Okay, so what I've done here is given like a new definition, because this is taking finite duration signals in and returning something of finite duration, of the same duration. So I'm sort of abusing notation. Before I used the circular convolution to mean you have two periodic signals and you get back a periodic signal. And now I'm saying, okay, actually let's think of these as finite duration signals, and you get back a finite duration signal. And their circular convolution then is the same as the circular convolution of their periodic extension. Okay, so mathematically what that means is okay, we wrap around the space when we flip and shift. So we could write out following. I keep introducing no notation because I don't have a much simpler way to do this. But let's define a function where I'll use this funny notation, just a bracket with a little t, to mean equals t plus kt, where k is chosen to be an integer such that the output of this thing is in the range 0 to t. Okay, I will plot this because I don't expect this to have made a lot of sense to everyone. Let's plot it. Here's t. Nothing complicated about what I'm trying to do here. Only the notation makes it look complicated. Here's t. Here's 0. Here's capital T. And what I'm going to do is plot this function that I'm denoting this way. Okay. And all it is it's just, it equals t, and then it falls to 0, and it climbs again. It's just the sawtooth waveform. Goes to height t, so forth. Okay, that's all we're talking about here. Why did I define such a function? Well, because now circular convolution can be written as xt circular convolution with y of t equals integral 0 to t of x of x of tau y of t minus tau in this operator. So all I'm doing is I'm saying, look, y of t minus tau can go outside of the range 0 to t. I just want to shift it back into the range. And this is equivalent to doing my flip and shift on y, but wrapping around. So so flip and shift now works like this. If I have my x of tau, which is something like that. I have my y of tau, which let's say is like that. Let's say there's 0t, 0t, and I want to do a circular convolution. Then for any given value of t, my y of t minus tau inside that operator is going to be basically, of course it depends on which particular value of t I'm looking at, but it's going to be something like this. I'll have flipped it. I'll put that in dotted lines. I'll have flipped it. That's flipping, and then I'll have shifted it. And the result will be there's t, I'll have wrapped around. Okay, so there's 0. Does that make sense? So a flip and a shift now wraps around this interval. And then, of course, I take this and I do it, and I multiply it by x of tau, and I integrate. All three of these things are the same calculation, except that technically here I'm not putting periodic things in and getting periodic things out. I can always just think of these as one period of a periodic function. Okay. So let me give you another reason why you care about this. I already gave you this reason, and that was that the multiplication rule for discrete time was a circular convolution in frequency. Let me try to justify another thing here. Consider the Fourier series. You may recall that we derived, before we even got to the convolution rule for the Fourier transform, we derived what was going to happen to a complex exponential that went through a linear time invariant system. That's how we kind of motivated this. And we found out that if we put in e to the I 2 pi ft, then we would get out, and this was a convolution with h, then we get out h evaluated at f of e to the I 2 pi ft. So that was what we did first, and then we said, oh, well, notice that if x is periodic, then that means that x of t equals this sum, the Fourier series. Now with the 1 over t up there. And that meant that the output, so x of t convolved with h of t, was going to equal, and we just applied it to each term in the sum. Oh, there's no 1 over t here, sorry. It's the inverse that I'm writing. Okay, so and that was just going to equal sum k equals negative infinity to infinity, and it was an ak, it was h of the particular frequency, which happened to be k over t, e to the I 2 pi k over t. All right. Now, let's look carefully at what if we interpreted h. So this is true. Okay. And notice we're looking at a periodic function with an aperiodic function. So imagine that h, for the moment, has a shorter impulse duration than the period of x, okay? Just to keep things simple, that means that that this function, ht of tau of t, the periodic summation, is equal to the periodic expansion of h, okay? Doesn't actually matter if it's longer, that's okay. Then we know that this is a circular convolution between x of t and that thing, right? And what we found is that there's a product rule now. So if you take the circular convolution of these guys, so these are equal, those are equal by what we saw above, then the Fourier series, let's write it like that, the Fourier series of that ends up giving me the coefficients ak h of k over t. last thing I want to point out here, so what I'm trying to show you is there is a product rule, there's a dual to the product rule, or I should say to the convolution rule for Fourier series as well. We have, in the continuous time Fourier transform, we had that convolution of two inputs was the product of the output. And here what I'm trying to show you is that the circular convolution of two inputs. Okay, so you might think of one period of x circularly convolved with one period of h. And that has a product relationship for the Fourier series. That you have ak times this thing here. And the question is, how does that relate to the Fourier series? Well, okay. So let's assume that h of t has a finite duration. Assume for now that zero to t. Okay, we talked about the Fourier series for finite duration signals. That's the first thing we talked about. And that means that the coefficients are coefficients. I don't want to use a for the coefficients, so I'm going to say b sub k equals the integral equals 1 over t, the integral of x of h of t, t e to the minus I 2 pi k over t, 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 and that happens to equal, because h is a finite duration, I can say that equals 1 over t, the integral from negative infinity to infinity of h of t, k over t, t, dt, and that equals then h of equals 1 over t, h of k over t. So what that means is that these terms here are simply, this whole thing simply equals 1 over t, ak, bk, where ak is the Fourier series of x of t, or equivalently, it's the Fourier series of one period of x of t, and bk is the Fourier series of h of t. Oh, you think capital T? Oh, yeah. Wait. Yes, you're right. So we have this Fourier series convolution property, but it's circular convolution. And this is actually important because when you do signal processing in MATLAB, what Fourier transform are you using? The fast Fourier transform. And what is that equivalent to? The DFT, it's the DFT, which is equivalent to the discrete time Fourier series. Okay? Because your signal is finite duration and discrete time. And so you're doing a discrete time Fourier series, which means that if you try to implement filtering or convolution by doing it in the frequency domain. Okay, so this you may have done this or have thought about doing it, saying, oh, I want to implement a low-pass filter. I'm just going to take the Fourier transform of my whole signal, and I'm going to zero out parts. I'm going to then go reshape the Fourier transform, and then take the inverse. Right? That's one way to do filtering. You have to realize that what you've actually done when you've multiplied the Fourier transform by some scaling factors, you've actually done a circular convolution of the so a circular convolution of the impulse response that you would get from your rescaling. Okay, I'm using too many words here. So imagine that your idea for filtering a signal is you're going to take the Fourier transform and you're going to multiply some of the coefficients by 2 and leave everything else the same, and then take the inverse. And you want to say, well, what is this doing? Well, we know that there's a convolution property that's multiplication in frequency domain. So why don't I just take the signal that's 1s everywhere and 2s where I multiplied by 2s. So that's a frequency domain signal. That's what I multiplied for to implement my filter. So why don't I look at the inverse Fourier transform of that thing, and I'll call that's my impulse response, right? And I've just implemented a filter with that impulse response. There's one catch. You've implemented it using circular convolution, not regular convolution. So so that means that the edges, as you do the convolution, the edges wrap around. Okay, so it's one catch to trying to do filtering that way. Okay, any questions about that, or should we just leave it mysterious? All right, let's do our 2-minute break and then we'll finish up. Okay, let's talk about modulation. Okay, so modulation is multiplying a carrier signal by an information signal. Okay. Now, usually, I mean, it's very common for the carrier signal to be a sinusoid. All right. So, what that means is, let's say you have some, let's say, x of t. So we're looking at something like x of t, which is our information signal, times some, let's say, cosine of 2 pi ft. All right. Now, I'll put f sub c here for carrier frequency. Okay. So what that means, if we were to draw this out, let's say that this is x of t here. So let's say x of t looks like this. Okay. Here's the origin. Let's draw this line. Our zero line. And let's assume that the carrier frequency is very high compared to the frequencies of our signal here. Then the result is a multiplication which looks like this. Oops. Which looks like oops. All right. And you get the idea. That's what the product would look like. Why do this? Well, imagine that your information signal does not, when you look at the spectrum x of f, the Fourier transform, imagine that it only has some limited bandwidth, and by that I mean the frequency content, at least the stuff you care about, is contained in some range. So here's 0, and you have some f bandwidth and minus f bandwidth. And it looks something like this. Let's say. And it's 0 everywhere else. Or you could say, suppose it's not 0 everywhere else, but for some reason you don't care about the stuff out here, so you first do a low-pass filter to get rid of it. Okay, so now you have it band limited. Okay, then when we, let's call this thing y. Y of t is the modulated signal. Is this a linear time invariant system? No, it is linear, but it is not time invariant. If you shift the signal, I mean, you know, if you make it fuzzy, then yeah, it looks like it's the same thing. But in reality, it's not going to line up. If you delay your blue signal here, then the phase of the carrier frequency is going to match up differently. Okay, it's not going to exactly be the modulated signal delay. So it's not time invariant. So what that means is we shouldn't expect, you know, it to behave like linear time invariant system, but we do have a multiplication property, right? So we know that y of f equals x of f convolved with the Fourier transform of cosine. What's the Fourier transform of cosine? What? Two delta functions, yep. So we have 1/2 delta of, let me see how I wrote this. Oh yeah, it's 1/2 delta of f minus fc plus 1/2 delta f plus fc. Okay, so that's the Fourier transform of cosine, and we get that convolution. So what that means is that this is going to look something like the following. It's going to be, you're going to have some fc here. There's f. There's 0 again. Got some minus fc. And when you do convolution with a delta, you just shift your signal over to that delta. So you're going to get something like this. And I'll just label this one fc plus f bandwidth and so forth. fc minus f. Okay. So there's now, imagine now that the bandwidth of your signal is, let's say, something around 20 kilohertz. Okay, that's sound, right? You don't hear well above 20 kilohertz. And the bandwidth, and let's say that the carrier frequency is like 100 megahertz. All right, then that means that this is so much bigger than this. This is about on the order of 1,000, right? 10,000. So what you're really looking at, let's say, so if x of t is audio, then f bandwidth is less than 20 kilohertz. Let fc equal, in fact, I'm not going to do 100 megahertz because that's the FM broadcasting range, but I want to talk about amplitude AM. So let's just say it's a let's just say it's 1 megahertz. Okay, then what you get is a picture that looks like this, where it's very narrow around your carrier frequency, right? "20 kilohertz is not that wide compared to that carrier frequency. Okay. Now, question is, can we get back our information after we've done this modulation? Is this invertible? Well, we could try to divide out the cosine, but instead, notice the following. What if we did so there's many ways you might try to get, so the punchline here is that this is basically how AM radio works. You just multiply your information signal with a carrier frequency that's very high. Now what's the purpose for doing this? I can pick another carrier frequency that's not too far apart, as long as they're the bandwidth apart. I can do another one here, and these don't interfere with each other. Okay, so I can transmit them at the same time. The signals add up in space, they add up in the antenna, but by linearity, the Fourier transform just looks like this, and in the end, I can filter out, I can apply a filter to get only one of them, and the other ones don't affect it. So tuning to a station, tuning is filtering. Well, it's not only filtering, but that's one step. Filtering and, okay. And so now I have a way of packing in a bunch of information simultaneously by putting it at different frequencies. Okay. So let's talk about how do we get back the audio signal from this. Now, there's an old-fashioned way of doing it that was based on trying to make very simple circuitry, and that simply said, let's do a peak tracker here. So the black is what's transmitted. And you could very simply, with the circuit, using just a diode, a capacitor, you can make a peak, something that kind of tracks peak. And it would go like this. And it wouldn't get you your blue back exactly, but it would approximately get it back. Between each peak, it would kind of fall, and then the next peak would pick it back up. You get you'd get the audio back with some noise added to it. Okay. Sometimes Boy Scouts will make these radio receivers because it's so easy. You can make a diode with a crystal, and you can hear radio, and you don't even need a power source necessarily. Nothing very sophisticated. Okay, but let's talk about how to actually get it back with better quality than that. Notice what happens if I take y of t times cosine of 2 pi f c t, the same carrier frequency. Okay. So, well, we could use trigonometry, but might as well avoid trigonometry at all costs and just look at the Fourier transform. So, what happens? Let's do the Fourier transform again. Okay, so that means that if we look at that Fourier transform, we say y of f convolved with, and it's the same thing again, 1/2, oh, I should put the half here. Okay, 1/2 delta of f minus fc plus 1/2 delta of f plus fc. All right, well, what that means is, let's go back up to this plot. So this is y. Now we convolve again with a delta here and a delta here. So when you take this whole thing and convolve it with the delta here, you shift it over like this. We get two things like this. Right? Similarly, when you convolve it with the delta there, they shift over here. And you actually get something. You can visualize that. You're going to get at 0, you'll get the one here. At minus 2 fc, you get a smaller one. Why will you get a smaller one? And at 2 fc? Because these, yeah, the one in, I'm going to draw that better. The one in the middle is, yeah, 2 of them added together. So let's say that's, so here what we had was height, I should say height 1/2 of the original height because it's a half delta function. And now you get one you get 1/4, you get 1/4, and then you get 2 1/4 added together in the middle, so you get 1/2. Okay. But the point is they add, they don't mess each other up. And now all you have to do is do another filter, a low-pass filter. Low-pass filter to get rid of this stuff. And you get back exactly the audio you wanted. Okay, so this is how you can demodulate an AM signal. You just do the same thing it took to modulate it. Well, first of all, you have to go, well, you don't actually have to. It may work out not to worry about this tuning. But you multiply it. But what you could do first is filter out all the other stuff. Actually, you'll see that it doesn't matter. As long as you modulate it again with the same frequency that it was modulated the first time. And that will get it back down to 0. And then you low-pass filter. You get back your audio.